Oh, you need to link. Haha.
Hello and welcome to Haskell Mask, the show in which we let you figure out what is the second word which completes the title of the show. Hello, Thurston. How are you?
I'm good. How are you, Sam?
I'm good. Uh,
So we have a slight problem. I,
oh,
I forgot you to send the Visual Studio Code sharing link. So I will do that now.
mm-hmm.
Um, and for some reason, it takes a while.
Well, while we're waiting, uh, have there been any new developments since last time? I saw on Twitter that you implemented other models than uh, Bart and T5 and Bert. You worked on something called Roberta.
Yes, that's that's true. I continued a bit this journey on implementing state-of-the-art pre-trained transform models. Um, And I looked at Roberta, I don't know how to pronounce it, and Bird, also partly driven by Austin, who also works on Hastorch and has made it possible to use Roberta through Torch script, which is a way to trace and well, basically, it's meant for interoperability between languages. TorchScript is some way in which you can sort of serialize a model in one language and deserialize it in another. So it separates a bit like the implementation from the runtime. And Hastorch also has uh, excuse me, Hastorch has also a way to use that. But the downside of this is that you have this complete black box, right? So like you're loading this model and then you have this function that you can call with inputs and that will give you then outputs. So you can do that too, but I don't think you will be able to train your model using that. So it's more like if you're done, if you're satisfied with your model and you just want to ship it to production, then tracing makes sense. And since we're interested in changing the model, like updating its weights and adding additional pieces, I think what we're doing makes more sense.
Mm-hmm.
Yeah, did you get the link?
I did. It seems to be taking a while to load. At first, it was because I think my version of the live share plugin was outdated, but now that I have updated it, it still says like loading file tree.
Mm-hmm.
So maybe we can use the time to recap where we're at. So we had uh, tweaked the well, we had you had previously like generalized the code so that we didn't have to tweak T5 into Bart, but instead could specialize a generalized transformer down to Bart, as you did with T5 and Bert. And we had done most but not all of the work, and then you realize that there was a big missing piece, namely the part that transforms the input text into a sequence of tokens. Any idea how we're gonna tackle that?
Yeah, so I looked into this.
Mm-hmm.
So Austin again has made some progress on that. So there is a proof of concept Haskell binding now for Hugging Face tokenizers,
Cool.
which is a Rust library. Um, and there's like a little shim that connects it to the Haskell world. The problem is I tried to add this to the repository today, and it took several hours to attempt that because I'm not a Rust expert. And I had some issues, and I could not resolve them. There were problems with linking that wouldn't go away.
Mm-hmm.
So since I'm using Nix here, that can be quite nasty to resolve. I think what I need to do is So like the issue plainly is that I'm trying to compile the tokenizers library, and the compilation step goes through fine, but at linking time, like basically last step, I'm getting an error that a library cannot be found. And I think that's because the path that the library is supposed to be in is not the correct one. And there is a tool chain or a set of tools one can use to resolve these issues. On Linux, this would be called patch elf, and on Darwin, it's
tool.
library name tool something. And I haven't really figured out how to use this yet. This was the last thing I wanted to do, but time was running out, so it's not working right now. But I think next time it will be, hopefully. But even without that, we can make progress today because we have still some pieces left. So I think last time we finished the Bart encoder, or we're about to, and we still haven't done any work on the decoder, nor the pieces that put everything together at the end.
Oh, I thought we were almost done. We're less than half. Okay.
Well, it should go fast now.
Okay. So if we do manage to finish all that, even without the piece in the Haskell ecosystem that reads the file, we should still be able to like use Python to convert the input file into a sequence of tokens and then feed the input sequence of tokens into our Bart implementation in order to make sure that we get the expected output?
Yeah, so for testing purposes, that is totally fine. And indeed, this is what I'm doing too at the moment, since I don't have the tokenizer. But if you had to do that for every input that you wanted to send to the model, that would not really be a good idea. So like long term, we need that library, actually sooner than later. But we will have it soon, I hope. And without it, we will just do as you just said. So basically, instead of like feeding a string to the model that then gets converted by the tokenizer to a list of IDs, we will just feed the IDs directly, and we will not see what these mean, right? So they're just like some numbers, but that doesn't really matter for testing purposes. You can basically feed whatever you want. It's just about that the numerics are sound, right?
Oh, you want to check that the numbers returned by the Python implementation are the same as the numbers produced by the Haskell implementation. Yep. It looks like I'm still having issues with the live share. Can you send me a new link or something?
Yeah, I will kill this and start again.
All right. So you said that we were done with one half, either the encoder or the decoder, and that we still had to do the other half and something else. So which of the two halves are we doing next?
Yeah, so I think we finished the encoder.
Okay.
So like if you look into that file now, no, it's missing. There is no instance for the Bart encoder, so we're not even done with the encoder yet.
Okay.
Okay, so I guess we have to do that. So there's still a nice pictogram for the encoder, but there's no implementation, so that's missing. So I guess we have to fill it. Right. So, but we can just follow implementations that already exist and make this easy and fast.
But I remember that we copied an instance that looked just like that with the forward implementation. So could it be that you're misremembering and that we did the decoder together rather than the encoder? Or that maybe we're not looking at the right branch, that we did the work, but you stashed it somewhere?
No, I'm pretty sure we...
Oh, right, but all of those other pieces that we worked on, such as multi-head attention, they also have an instance with a forward function. That's really the one I remember.
Yeah.
Because we only did one. We did the one for multi-head.
Right. I think if you took the Pegasus implementation that is at the bottom of the file and changed it slightly for Bart, then I think we can call this
yet done. Another one, Pegasus. So Pegasus is closer to Bart than BERT
Yeah, so
and
this one is a
T5?
bit closer. So like I worked ahead a bit and did this Pegasus, and
Mhm.
Pegasus is actually done. It works. And from an architecture perspective, it's almost identical with Bart.
Cool.
A few things that are different or a bit quirky, but it's very close to Bart. And since Pegasus already works, I think we can get Bart running fairly quickly. So Pegasus is a summarization model. So in goes sentences, paragraphs of text, out goes a summary of that. So it has been pre-trained on a dataset, or for instance, a dataset called extreme summarization, or XSum,
Mhm.
where the summaries are extremely short. I've used that recently. So it's a very nice model, but it's also very big, so it doesn't run well on CPUs.
Okay, so one of the things we'll have to tweak for BART is not just the number of not the number of layers, like the order in which the various layers are stacked, but also the numbers that indicate how big the matrices are and number of layers and things like that.
I think we will have to do that, but we don't need to do that now. So like the implementation that we have here is extremely generic. So it works for all sorts of parameters that the pre-trained model could have. So like starting from the data type to uh, the embedding dimensions, input dimensions, feed-forward network dimensions.
Yeah, I'm sure
So all
all of
these,
those things are parameterizable. I just haven't
yeah, they're
seen
all.
where we are parameterizing them yet.
Oh, okay. So the way in which I thought we do that here is so there is always a um, common part for these models, and then there is a specific part for the individual pre-trained versions of them, right? So like if you say the BART model, it's
Mm-hmm.
not really clear what you mean. Like, do you mean BART architecture and like the source code of it? Do you mean the pre-train one of the pre-trained checkpoints, and there are many? So then it's also not clear which one you're referring to. So, um, but so like here, when we look at uh, the BART constructor, right? So like this basically this tag, transformer style tag that says BART, and we're talking
Mm-hmm.
about the BART architecture and implementation, right?
Mm-hmm.
We're not talking about a specific um, configuration of all these parameters. And I've made a small stub. It's called base.hs. You will find it um, in
Yeah, I'm
transformers.
still following your mouse.
Okay, cool. So at the moment it's completely empty,
Mm-hmm.
but we could compare that with Pegasus
Oh, numbers.
.hs. So here's an example for Pegasus, right? So you see, okay, Pegasus has, for this particular model, has 16 layers, both in the encoder and the decoder. 16 attention heads, 64-dimensional head embedding dimension, and so on and so forth. So we will have to find these numbers for the BART model we want to use, and just make these types, and then have this type synonym at the end. So like there are two that make sense. There's just the bare model itself. So if you have only that, then what you get back is just the hidden dimensions of the last output layer of the decoder. That is extremely generic, but also extremely unhelpful if you want to use this to create text. So if you wanted to generate from this, you need a additional component. It's called a language modeling head. And what that does is basically just so like the representation that comes out, I think for Pegasus has 1024 dimensions, but what you actually want to have is a representation over the whole vocabulary, right? So like you need something in the case of Pegasus that has 96,000 dimensions, because there are 96,103 different tokens in the vocabulary. So if you wanted to have a distribution over them that you can sample or really select one, you need to project, or like you have to basically blow up the output dimension to that space. And that's called the language modeling head.
So you said there's 96,000 different tokens. So I would have expected that we would need like a vector of size 96,000 with one number each with one hot encoding. But now you said that it's 96,000 dimensions, which is quite a bit larger than a vector with one dimension of size 96,000.
Yeah, so I meant, of course, the latter.
Okay.
Yeah, 96,103 elements in that vector. Yeah.
Okay. That sounds more reasonable.
Right. So, but we're not there yet. You can do that now if you want. But yeah.
Because like you said something surprising a few minutes ago, and I just wanted to repeat it back in order to make sure I understand. Earlier in the project, you said that we wanted to reproduce exactly the Bart model in Haskell so that we could load a snapshot. And I now understand that this means we need to reproduce like 3 different levels. We want to have the same architecture, but we also want to have the same, I think they're called meta parameter, like the numbers we're currently looking at about the number of dimensions, hyperparameters. And then what is, if we have the correct numbers and the correct architecture, then there will be the correct number of concrete individual floating point numbers that we'll be able to load from the file, from the snapshot, in order to also not just reproduce the same architecture and the same hyperparameters, but also the same behavior as the pre-trained BART model was snapshot we are taking.
Yeah. So so like, I mean, of course, this goes all hand in hand. So these are actually not 3. I mean, you can see them as 3 independent pieces, but changing one of the 3 will break everything, right? So like, if you change the model implementation, the snapshot or the checkpoint that you want to load doesn't work anymore, right? It will produce wrong numbers, right? So this is what we actually want to avoid. That's why we do that test, right? If you changed the hyperparameters, for instance, here for XSUM, the Pegasus XSUM model, you can't load the checkpoint anymore. You will get an exception that the dimensions don't line up, right? So you immediately are blocked from using the model. And if you change the weights of the model, well, then you also get garbage, right? So like, I mean, all these things work together, and we have to line them up in the right way.
I see we have a rare opportunity to interact with the chat by explaining the title of the show. So it's Haskell Mask, of course, not in reference to the Jim Carrey movie, but in reference to the fact that in those models where we are trying to complete a sentence, or we're trying to complete Haskell code eventually, we represent the question to the model as a partially completed sentence, like all of the words we have so far, with the special token mask for the part that the computer is supposed to fill. So it would be like in the middle of the sentence, but if we want to complete it, then we would just put it at the end. And so Haskell Mask is a title where you have to figure out how to complete the name of the title. All right.
I'm really curious actually what the answer is. Is it cat?
That's what I was thinking.
Okay. Should we get cracking?
Yes, please.
Cool. So
encoder.
Yeah. So like, maybe we want to go back to encoder HS, and you could grab the whole has forward block for Pegasus and just copy paste it above into that gap that you left for Bart.
Sounds good. And where is it? Oh, here. There's a diagram without an implementation.
That's the wrong one. Slightly wrong. So I made two holes, one for Bart and one for mbart. You will probably not need mbart, but just in case, I left it there too. So mbart is multilingual Bart. So if English Bart is not good enough for you, and you want to use these models on multiple languages, maybe mbart may be the better choice. Right. So right now, Haskell is complaining a lot because the implementation is in conflict with another already existing one. And,
yeah, I'm renaming Bart
just
to Pegasus everywhere. And what's the next error? Okay, so the squigglies are in the forward implementation. So I'm guessing that the order of the layers is not quite the same as with Bart. Let's compare the diagrams.
Yeah, so I don't know exactly which one you were looking at now, but if I went in line 778 and looked at what the error for forward TE pos enc, so that stands for Transformer Encoder Positional Encoding, is, then I get something like could not deduce the hash forward instance for this weird TE pos enc f of Bart.
I remember
there's
that.
a hint here what's going on. There's the hint what's going on here. So TE pos enc f is a type family,
which we probably need to duplicate for Bart as well.
Here. Yeah, so it's stuck here because there's no entry for Bart yet.
TE pos enc f. Go to definition. There's an instance for T5, Bart, Roberta, and Pegasus. In which order do you usually put those? Is there another instance of Bart?
I think. Yeah, I'll just put it somewhere.
Okay.
I will make a noise now. Don't freak out. It's not a beer. That's 7-Up.
I already forgot what I previously searched for. TE enc, no, pos enc f. Definition. I'll put it between T5 and Bart. I should not be copying T5. I should be copying Pegasus because you said it's closed Pegasus. So let's put it.
Yeah. So if you look at the differences between T5 and let's say Pegasus, there's a small but important one. So like for T5, we're using pos enc dim, right? And het dim. So like the embedding is between positional encoding dimension. So this is the dimension of the encoding of. So what is the positional encoding? If you're not familiar that much with transformers, there is something that is worthwhile remembering. Without providing positional encoding, the transformer does not know in which order you're submitting anything, and that's because there's no encoding of it. So like if you don't have a way of encoding or telling a model in some way which character or which token comes after which other, it will not have any sense of ordering. It will know that these are different tokens, but it doesn't know which one is ahead or after the other. And
that is quite surprising to me because I would have expected that the input of the model is like a vector of numbers representing all of the tokens, and so it should be able to treat those at the beginning differently from those at the end. Is it something like the convolutional layer where all of the pieces are forced to be the same, and so it cannot treat those at the beginning differently from those at the end?
You could say that. It's okay. So like all the mathematical operations in the transformers are such that they're invariant under permutations of inputs. So that's the and of course like so I say that because
cat pushing things
of course
off the desk.
if you have sensitivity of with regards to ordering in actually I think what I said makes sense. Yeah. So like the only thing it can break the symmetry is a positional encoding, right? So like we have the token embedding, which looks at the token index. So like, okay, so we go from sentences to words or subword tokens, and from the word pieces which are still strings, we go to numbers, and from these numbers, then we go to a row in an embedding, right? We can do the same thing also with the numbers that just count from 0 to a length of input vector, right? If you just had a range of numbers, of natural numbers from 0 to length of input vector -1, you can just also index into an embedding, pull that out, and give it to the transformer so that it can do something with it. And there's a difference in how T5 does this and how Pegasus does, and how Bart does that. Pegasus and Bart do it the same way. Also, Bird and Rubella do it in the same way, which is you have an absolute encoding of positions, meaning like you actually go 0, 1, 2, 3, 4, 5, and so on.
And then the model has to learn that like the difference between 2 and 4 is the same as the difference between 4 and 6, and so they have to learn the same thing all over again?
Yeah, so interestingly, I think for Bart, although don't quote me on this, I think for Bart, the positional encoding is learned, meaning you start with random numbers in the positional encoding, and then learning what position 0 or 1 or 4 or 5 means is actually learned during training. In BERT, this is not the case. In BERT, you have a sinusoidal encoding of position, meaning that the embedding weights for the position encoding is frozen. So there's just a function imprinted into these weights in such a way that the output is sort of nice, has nice properties for learning. You can look in the original transformer paper on how that works. So basically, it's like a superposition of different sine cosine function at ever increasing frequencies, and that makes it possible for the model to quite easily distinguish between positions in the input. But I think for Bart, these things are learned. But since we're loading already a trained model, we don't have to worry about that. We can just use these embeddings as they come. The only important thing is that we have absolute positional encoding, and the maximum supported position is 512. Actually, 511. So we have 512 positions we can support. If we have one more, then our model won't be able to handle that. So we are forever limited to 512 tokens.
Whereas with the sinusoidal encoding, it sounds like we can extend it, because a sinusoidal can be extended.
Yeah, we can. So the sinusoidal encoding could, in principle, be extended to infinity. The problem is just that if you did that, since the model at training time has only seen these encodings up to 512, it will probably not generalize very much to larger numbers. So if you have a larger input than 512, all bets are off. It may work, it may not work. So there's some research on that, but more recently it turned out that relative positional encodings are better, and this is what T5 is using. So in relative positional encoding, as the name suggests, you don't have an absolute encoding of numbers 0 to 512, you have, or 511, you have a relative positional encoding to a certain horizon, which I think in standard T5 is like 32 tokens or so. And then you also separate into buckets. So like you bucket things that are closer together. You don't bucket them, sorry. So like the model basically sees things very clearly that they're very close to the position. And then the further you go away, the more coarse everything becomes. Once you're very far away, it doesn't matter where exactly this is, just far away. So this is kind of like how this works. And then you get away with a smaller encoding. So you only need to encode ever 32 different positional.
Cool.
Yeah, and here we have 512. So it's smaller, more efficient, works the same, and probably, or possibly, or even, I think, empirically, this generalizes better than absolute positional encoding.
Because if you have more data, you can just put them all in the furthest away bucket.
Yeah.
So I have a question. You said the word embedding quite a few times. Since you said lookup in the embedding, I'm guessing that this has to do with the fact that in the transformer there's a weighted key that we look up in order to get a weighted value that gets averaged out. Is embedding a fancy name for the weights of the matrix that we're using when we do this lookup?
So like embedding lookups are not attention lookups.
Okay.
So attention lookups are soft, right? So there is okay, so they're soft, and embedding lookups are hard, meaning that like
because you have a single key.
It's literally you key into a row, into many rows of embedding vectors that all have the same.
And
size.
those rows is like you have a matrix of values that are learned just like all of the other parameters. Okay.
Yeah, so it depends on the embedding, right? So like for the token embedding, you have everything is learned, except I think for the padding token, typically, not always, but typically the padding token with special is always set to 0.
Mm-hmm.
Like all entries are 0 of that vector, and they're always staying 0. And for the positional embedding, depends now if you're like Bart style or Bart style. So like if it's Bart, then you will find these sinusoidal encodings in there, which are permanently fixed, or sometimes they're learned, right? And then there could be any numbers in there.
I like the idea of hardwiring as much of the architecture as possible in order to help the model in the direction we want.
Well, it all depends on how much data you have, right? So like if you can afford the luxury of spending some of your training data on learning positions, sure, go for it.
Okay. Well, we don't have the luxury of choosing whether we want to hardwire or learn. We have to use the exact architecture that has been used for the Bart snapshot that we want to use. So, okay, finally back to the code. I copied the Pegasus encoding. Is there any differences between the Pegasus and the Bart encoding for this particular function?
So staring at the diagrams, I don't think so. They're pretty much the same.
So how does the type family we're looking at relate to the diagrams?
Wait, which type family are you looking at? The TE Posenc?
Well, yeah, we were fixing the first error by adding an entry for TE pos enc f, and then you mentioned the difference between T5 and Pegasus, and that led us to this long side discussion. And so that's why before moving on, I want to make sure that I didn't just blindly copy Pegasus and hope it's right. How do I know whether there are some subtle differences between the Pegasus architecture and the Bart architecture that makes it so that this type family needs to be defined slightly differently. But I don't even know what this type family is for, so I have a hard time looking at the difference between the two diagrams and figure out whether those two definitions should be the same or different. So what does TE pos enc f do?
Okay, yeah. Basically, this is some sort of like dispatch mechanism that I came up with. So we have a generic transformer encoder, which is basically just a container for 5 different things: a stack, an embedding layer norm, another layer norm, dropout, and positional encoding. So these 5 things, and there could be anything in theory, right? So there could be nothing. Each one of them could be nothing if they're not present. So nothing would be encoded as a unit. And so unit because we need just some filler value. We could use anything. I guess unit makes sense because it just has one value. So from the convention here is to use unit to indicate that layer is just not present.
Okay, but the nothing that we see in the type family has nothing to do with the nothing that you are talking about that gets converted to a unit, because I see that those are all dimensions. So a nothing indicates that we don't know the dimension, in this case.
Oh,
Or
you specifically talking about this value. So I shouldn't say value, it's a type. So you defined this to be embedding of layout dense, device, data type, post enc dim, input dim, nothing. How are we sure that this is the right definition?
oh, right. Okay, so this nothing is not the instance, the value we pass for pose enc dim. The value we pass is this pose enc dim. Okay, so we are using this value to construct encoding, and encoding takes a maybe nat as its last argument, and that's why we give it nothing there. Okay.
Yeah.
So
what does this
embedding
maybe
is the general thing that can be specialized.
Right.
Okay.
As it turns out, in many cases, it's just the same. But to be honest, like when I came up with this way of encoding, I did not know which models will turn out to be identical. And in fact, actually, there's nothing that you see at the end. I'm not sure if this will remain nothing for these. At the moment, it's not important. But what if this was just of a nat, then we would have to figure out what that nat should be. What is it used? What is it used for? You can tell the embedding layer to treat a special index specially. And you typically do this for the padding. So if this turns out not to be nothing, then what you can do is you can treat the padding. So let's say you want to train your embedding, right? But you also want to constrain the padding token to always be 0. Even if you update all the other weights in your embedding layer.
Yes, I do want to wire in some things, yes.
Yeah, so you still want to like preserve the fact that the padding token is always 0, always mapped to a bunch of zeros. And with nothing here, you turn this off. So that means the padding token is free to become something else, but only if you train that thing.
Okay.
If it's turned to just, let's say 0, if the padding token index was 0, then you would encode that you don't want this row of this embedding matrix or tensor to change. I didn't care about this yet because we're not training this thing or fine-tuning that thing, so it doesn't make a difference right now. But if you were to do that, we will have to look closer into whether or not we want to allow change here. At the moment, we do. Maybe that makes sense, maybe it doesn't, but for right now, there's no problem with changes to nothing.
Okay, I see there's a question in the chat, but I have one more question before that. So this word embedding here that you said is the generalized thing, it doesn't contain the word encoder in it? So is it like general enough that we can use it to specialize it to an encoder of all of those different architectures, or a decoder of all of those different architectures, and maybe even other things? Or is it just because it's local to this file?
So where do you see the word encoder?
So on 188 in encoder.hs, we are defining te-pose enc-f. I assume enc is for encoder. And we define it not as like encoder embedding, but as embedding of something, something, something. And so that's why I'm asking if this embedding thing that you said is something general that can be specialized to a number of things is sufficiently general that it can be specialized to an encoder or a decoder. Presumably that's what te-pose enc-f is computing, the encoder of something, no?
I think we lost a bit here. So like
sorry.
So that the encoding part of posenc just refers to the positional encoding. So we're only talking about the encoding of positional information at this point. It has nothing to do with the encoding layer.
Okay.
Or even the encoder. So if I talk the encoder, I typically mean the transformer encoder, which is a really, really big block of things, of layers.
Yes, that's why I was surprised that we had something that could be specialized about. Okay.
No.
That makes more sense.
Like the positional encoding is really like the first thing that happens before it goes into the encoder proper. Right?
Okay.
So like you feed this to the first layer of the transformer stack, and then never again. So this is really early on, and then you're done with this. It's like a shallow embedding. It's just one layer. Nothing much happens there. You just index into these rows of vectors and then pull out the right one at the right position, and you're done with this, and then you don't consider it again. So like it's only positional information that we're dealing with here. And as I said, there are 4 other pieces here that we still need to set. These are the dropout, the layer norm, the embedding layer norm, and the stack. We haven't done it yet.
Yeah. But so now that you've corrected my misunderstanding, I have a new hypothesis as to the purpose of this TE pos enc f type family. It is that you have written elsewhere in this file the generic encoder, and the generic encoder has a bunch of steps, and in order to figure out what to do at each of those steps, you're calling a type family, and it just so happens that a positional encoder is always an embedding of some sort, and so that's why they're all equals to embedding, but it could be something like a fully connected layer or any other kind of layers. Okay, cool. Let's go to the chat's question. Thanks for streaming. I'm starting to write my bachelor thesis at the moment with the question about whether Haskell might be better with NLP machine learning than Python. Do you have any tips on where/how to start? Greetings from Germany. That sounds like a question for you.
Thank you. Greetings back from Canada. I would not go for Haskell at this point, especially like if you. I mean, even if you're doing a bachelor's thesis, you're looking for. You want to make progress, right? And you want to go into an environment where you can be productive very easily, and there's a lot of training material available, and you can just like look what other people have already been doing and extend from that, right? Therefore, Python would be my suggestion at this point. Unless you really know what you're doing and you're doing something that nobody else has ever done, and you have reason to believe that Haskell is the right choice, and then you may go that direction. But otherwise, I would stick with Python because this is what the absolute majority, like 99% of machine learning researchers are using. And no, I mean, Haskell is not there yet.
I am enough of a Haskell snub that I definitely want to stick with doing machine learning with Haskell, but I don't have very big ambitions for what I want to accomplish. I just want to learn how this works. I know you have bigger ambitions than me.
I mean, I'm doing this also because I want to. I mean, like now, really, if somebody asks, do I want to use Haskell for this? Typically, I have to say no, but I'm working towards not having to say no anymore, right? Or a little bit less so.
Well, now that you made it so much easier to encode models than before, because we can specialize the generic architecture you wrote to a specific model, it sounds like we're one step closer. And as you add more and more entries, and as eventually we'll finally add Bart, we'll be one step closer still. But I imagine that if like here we have like 5, 1, 2, 3, 4, 5 models that once we're done with Bart will be provided out of the box by HaskTorch. But if you use Python, you have probably like 1 million instead of 5.
Yeah, these are just transformer models, right? So like depending on what you're doing, you might maybe come up with a completely new architecture, or you may compose from different sources, right? So like the coverage that HaskTorch at the moment has is very, very small compared to what you would get, let's say, PyTorch implementations on the internet out there in some GitHub repositories, right? Of course, you have to be careful because sometimes things that you find in someone's GitHub repo are just wrong, and you don't know it, right? But if you, let's say, go to a webpage called paperswithcode.com or so, and you look up papers there, so this webpage tracks basically which publications come with implementation, which is open source and available. And these implementations typically are good. This is actually a nice way to find also, like, it's also organized in terms of like benchmarks, right? So if you're looking at some benchmark for some task on a certain data set, you find which models are the best at the moment and their ranking, and then you can also see where the source code is, if it exists. So if you're looking for guidance in terms of that, just go with that as probably the safest bet. And if it's NLP, then I guess the Hunger Phrase Transformers library is extremely good in getting started.
It's exciting to get to interact with the chat, but let's try to go back to the code. So now that I finally understand the type family, I understand that TE_POS_ENC_F is describing which layer we want for this TE_POS_ENC part of the diagram. Oh, I'm looking at the T5 diagram. Part diagram also begins with the TE_POS_ENC, but looking at the diagram will not tell me whether we wrote the correct layer in the TE_POS_ENC_F function. For that, we'd have to look in the Python code.
We will have, yeah. I'm not sure if I can bring you there quickly. So like if I open this, would it show up for you?
If
I have it open just
click
now.
on the button to follow you, yes.
Cool. So this is like the Bart model now, and the piece that is relevant is the encoder piece, and I have to find it first. I guess Bart encoder will do it. And Bart encoder layer, Bart encoder. Well, there's an embedding. That's the first thing that happens. There's a pattern index, so maybe nothing is not good eventually, but it doesn't matter right now. And then when it comes to putting all these things together, there is, let's actually compare the Bart diagram and the implementation. Maybe you want to bring them side by side. So that would be line 710 in encoder.hs and about 750 or so in the Python.
750
in Python.
Okay. So now you want to compare the diagram to see if the diagram correctly represents what the Python code is doing?
I think this was
a while ago.
I had done this, but you questioned its validity, so I would.
No. What I wanted to double check, since we had just written new code, like I assume that when you created this diagram, you double checked its validity with Python. What I wanted to double check is that the line of code that I had just written was correct, right? I copied the Pegasus definition of the positional encoder, but I have no idea if the Python code for the Pegasus encoder is the same as the Python code for the Bart encoder, positional encoder, and therefore the Haskell code should be the same as well.
It is. So the...
Okay, I trust you. We can move on.
But like, make no mistake, like what you just did was just telling the compiler what the constructor of that field should be, right? Mm-hmm. You didn't tell it how to use it. This is part of the forward method that you copied from Pegasus earlier.
You said, I told the compiler which constructor, do you mean which type?
Yeah, so like the type family basically just says if you wanted to create a value of type transformer encoder Bart, then when it comes to the positional encoding, use embedding blah 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 blah. Right. So this is kind of like what you just did.
And what will it use it for? Like, is it constructing a field in a record that I can now access in my forward function? Okay.
Yeah, exactly. That's exactly what happened.
I need to call it, and the first thing I'm calling forward with TE_POS_ENC and no parameters. So it doesn't seem like I could screw this up.
No, that's good actually, because the compiler told you what was wrong, right? It told you that the positional encoding was not defined. Couldn't actually it told you that there wasn't an instance for has forward, but it also told you that the type family was stuck.
Yeah.
And therefore now it should be unstuck because we added this additional type family instance.
There's no
and
squigglies
I think
anymore.
so if you hover over it, it should tell you now that this is an embedding. Actually, I'm surprised that this instance works right now because I don't think we were done.
Okay. But you said it was the same. You said that the Python code for the positional encoder for Pegasus and for Bart are the same. And so since I've copied both the definition of te pos enc f from Pegasus to Bart and the part, well, the entire forward function, like including the part that calls forward te pos enc from Pegasus, shouldn't that work? Well,
Yeah, everything is good.
okay.
We're done with posenc, but it goes on, right? So there's then the next line is add the input to it. Then there's something about dropout. Then we call this the encoder stack, and then there's layer norm. And I'm not sure why, but I expected a squiggly line under the layer norm, but Haskell
Perhaps
doesn't give me one.
so. Is it because you're so familiar with the diagrams that you know that there is a layer norm for Pegasus but not for Bart or something like that?
I did know. I mean, I do know that there is a layer norm for Bart, as there is for. Wait a minute. Actually, no, I'm not sure.
Roberta Pegasus. So the diagrams look indeed slightly different around the layer norm. The layer norm is before the dropout for Bart, but after whatever TE stack does for Pegasus. So yeah, there should have been some squiggly lines.
Wait a minute. So you're saying layer norm embedding. Sorry, I have to read my own code here. So like st5, there's Bart.
Can I just move it?
So we have so like if I look in the Python code, on line 680 there is layer norm underscore embedding, right? So that means we have an embedding layer norm. We don't have a layer norm, we have an embedding layer norm. So the difference is that the embedding layer norm is before the stack, and the layer norm is after the stack. It seems like in the Bart source code we don't have a layer norm after the stack. We only have a layer norm before the stack. Oh, and actually now I'm getting squiggly lines. That took a while.
No, I moved the layer norm before the dropout in order to match the diagram, and that introduced some squiggly lines.
Oh no, don't do that. Can you do that, please? So the reason why this was a bad idea is I accounted for the fact that sometimes you could even have both, right?
So it's a different kind of layer norm.
And after, yeah, so you could have one layer norm before and another one after, and even have different parameters in there, right?
So I should be deleting this line because there's
leave it in. So the correct way
of to make progress.
The correct way with dealing with this is adding a call to embed layer norm above the stack. So if you scroll down to Bert, line 887, there is an example of how to do that. Yeah, so if you copy this piece and add it above, right, and now you can actually delete line 785 if you wanted to. You don't have to, but you can. Okay, so why do we have sticky lines now? The reason is we haven't told the type families yet that we want an embed layer norm. And that's actually why I was confused earlier. I would have expected more errors before. There were, but there are none, or were none. So if you look at TE embed layer norm F, there is no entry for Bart, and we need one.
Oh, but this time I can't just copy what happens for Pegasus. Let me copy what happens for Bert.
Yeah, that should be good. And then below in TE layer norm F, you could make a new entry for Bart and give it unit.
Okay. So even though there was no entry, it was type checking before.
Yeah, that's odd. But that should be it. So I think we have a Bart entry now for everything, right? So like TE stack F has a catch all instance. in embed layer norm, we have a BART entry. In layer norm, we have a BART entry. Dropout has also a catch-all instance, and posenc is what we did earlier. So I think we're good there. But we have to repair now the type errors in that instance below. And I think what we could do here is
Same as
since I
usual,
think
delete the part that's not working and ask for the type error and paste it in.
yeah, or we could use the fact that Bird apparently is closer to what we want than Pegasus was, and just copy paste the constraints for that instance from Bird and replace Bird with Bard everywhere, and then the errors should go away.
So you want me to copy which part of the BERT implementation?
Just the
All of that.
constraints for the instance.
Okay.
Yeah.
Not fewer squigglies, only the TE stack part. So let's see if Bart, BERT, and Pegasus differ in that regard. So the TE stack receives the dropout and the unsqueeze, whatever that is, in Bart. In BERT, same thing. And in Pegasus, same thing. It receives from TE dropout and unsqueeze. So I don't know what's wrong. I should have asked Haskell instead of guessing. What's the error?
Have you changed the word bird to bard
Where?
in what you just copied?
Oh, I didn't realize there were instances of BERT in there.
Oh, that type checks.
Cool.
Cool. Okay.
So that's
I think
the
we're done
entire
there.
encoder?
We need to do something more. Okay, so hopefully this works. I open the terminal now. And in that terminal, I will call thing that loads the BART weights. Oh, it's not enough folder. And hopefully this is working for you. I mean, it's shown for you. Mm-hmm.
Hello, my name is Mask. What are we supposed to figure out now? I seem to remember we were looking at that last time in order to figure out the mapping between the names of the various layers. Is that still what we're doing?
Mm-hmm. We have to do this now for the encoder as well. So we're doing that for the pieces that are in the encoder. This is what we did last time. Now we have to do it for the encoder itself as well. So basically we're working our way up now. So what I'm looking for is model.encoder. So this is in the latter half. And we just need to confirm that the path is correct. So it should start with model.encoder.layers.
I don't know where in the Haskell code you expect us to modify the name of the layers.
In Lookup Encoder. This is line 570, approximately.
Oh, I see a bunch of squigglies around that place. Why do we get squigglies here?
I turn on all warnings including the one that says incomplete pattern cases. No, what is it called? Pattern matches are non-exhaustive. So
Oh, cool.
these functions are, yeah. It's a bit annoying because now everything is orange, but
But that's what I want in a good compiler, telling me when I'm not done writing the code. Thank you, compiler. Let's see. So now it would be very helpful to see the diagram as well. That's Bart. Okay, so we have all of the pieces. Stack. That's the last part. And it's defined.
yeah. So this lookup encoder for those who haven't watched us last time. So lookup encoder is a helper function that okay. So like when you instantiate the model, we can either initialize the parameters of the model randomly, or you can load it from a file, right? When you load it from a file,
I remember
typically
using those names. Okay, so we don't need to look at.
I'm just gonna for listeners or viewers, just gonna say quickly what's going on here. So like, lookup encoder is loading from a file, and the way it's doing it is basically just saying we want to construct a value of type transformer encoder. In order to do so, we need to create first values of all its members, of all its record fields. And the first field is stack, second field is embed layer norm, third field is layer norm, and so on and so forth. So basically, we have to recursively now tell Haskell how to assemble a value from other values. And for the stack case, we need to figure out when we have a file that's, in this case, coming from Python code that contains all these weights that we want in our model, where to find them in a dictionary. So we have this prefix there, and we just have to make sure that the prefix matches what we see on the in the terminal right now. And I think just saying layers dot is not enough. I think you want to add the word encoder as well.
I didn't know where we were starting at.
Yeah, so I think this should work.
If we're starting from the very beginning, that maybe it should have been model that encoded layers. It wasn't.
Yeah, so like we will have the model, and then we will have the encoder. And right now we're building the encoder. So I think actually, yeah, we have to just keep in mind what we do later on when we go one layer higher.
Sure. Embed layer norm.
So yeah, we have an embed layer norm, and this one is called layer norm underscore embeddings, it seems.
Mm-hmm. Oh, that's Bart.
And doesn't have a final layer norm, so we need pure there. And it has dropout, but we don't need to care about dropout because it's all the same for every model. But we have the positional encodings.
Embed positions.
Yeah. So it's funky. So this thing has dimension 1026 times 768. It's odd. Anyway.
So it's still orange? Even though we filled it for everything?
Probably it's still orange because I've defined more values than just these 5. Mm-hmm. So there's also GPT2 and I don't know what, an mbard. it won't go away until all these models are implemented. I guess it's
Okay, so the compiler is not telling me when I'm done helping you with Bart, but it's telling you when you're done implementing all of the models you care about.
gonna stay like this. Wait for any of that. I think we went encoded
I'm losing you.
are you still there?
Now you're back.
Cool. The stream was also interrupted for a few seconds.
Oh, then it was on my side.
Maybe this was my problem then. Anyway, okay, so we have the encoder now. Let's go to the decoder maybe.
Oh, we're done with the encoder. Cool.
I think so, because we have built already the stack and all the layers in the stack last time. And I think with the decoder we can be quick now because this is exactly the same pattern again. There's just one additional piece, so we have actually exactly the same pieces again.
All right, so we have a diagram.
I think
for
I made
Bart.
a picture. I made a picture for Bart last time. Yeah.
Yeah. So let's see which diagram is closest to. Is it closest to Pegasus again? It's almost the same except for the embedded layer norm. Let's just compare it with Bert.
Yeah, I would use the Pegasus one.
Yeah, okay.
Because the T5 one is too weird.
Okay. Copying this whole instance for not mbart but Bart.
Okay, tons of red.
Renaming Pegasus to Bart. But aren't we going to have to copy this whole constraint from Bart again?
Yeah, there is no decoder for Bert, so we don't have that luxury this time.
Okay.
I think this time we have to work ourselves.
Okay.
But I think the first line of
is going to be missing the type family.
Yeah,
I can
I think
figure out how to get Visual Studio to show me the error message instead of the type of forward. Cannot deduce as forward of td pos enc f. That's the same thing as before.
TD instead of te, we have td now.
Enc. Ah. So the word encoder was there, but it was not enc, it was e. Same as Pegasus again, I assume.
So then maybe you just create the instances for embed layer norm and layer norm as well, so that we don't have to do it later. I don't know why is a bird one? That doesn't make sense. I should delete that one. Where's that bird one? There can't be a bird. Let me delete the bird one. That doesn't make sense. Well, actually, you can probably rename the bird one to Bart. Just go ahead and rename bird to Bart.
Where?
Where are you now?
Well, you told me to rename something that relates to Bert to Bart. Which thing do you want me to rename from Bert to Bart?
I'm staring at the type family instances that start with TD. So there's TD stack F, TD embed layer norm F, TD layer norm F, TD pos enc F. And in 3 out of those, there is a instance for the Bert transformer style. As I said earlier, Bert doesn't have a decoder. Therefore, it doesn't make sense to have Bert here. But Bert and Bart are somewhat related. So I think the quickest way to have instances for Bart is just to rename Bert to Bart in these instances. Yeah, like you did just now. There's another one in layer norm, and that's it. Yeah. Ooh.
Oh, there's a big one here. Has initialized td pos enc f. Didn't we just do that? No, it was td pos enc f, not has initialized td pos enc f. Should we rename that one too?
We don't. Yeah, we could. I wouldn't care that much about this.
Okay, I'll leave it alone.
Cool. I think we're almost there. So now we have tons of errors. I'm there because of the layer norm. So maybe let me quickly try to repair this. So like in the end of that has forward instance, we again have the layer norm, which we have defined as a unit. So we can get rid of that one and replace it, or like put it somewhere else. It needs to go before dropout.
It's the embed layer norm, not the
now.
td layer norm.
And like.
And last time we were able to copy it from Bert, but now we can't. So you have to know how it's called.
I'm thinking maybe we can just copy, to be quicker, we can maybe copy a bit from the encoder. Because the beginning is the same. Just goes on. It's a bit different. Right. So we have.
Yeah, you want to copy the te embed layer norm. Oh, I think you already did it. Yeah,
okay.
It's td instead of te. Okay.
Oh, wait. Why is this?
Okay.
So it's complaining because pieces don't line up yet.
What's complaining?
Generate outputs.
Should we again copy paste the
yes. I think
constraint from somewhere else?
No, I think it's safer to try to fix this ourselves right now. Trying to see what's going on. So like we're getting a big error here because HasForward is a type class with functional dependencies. Mm-hmm. So output and generator output have to be always defined in a way where they follow from all the other type parameters. Mm-hmm. And at the moment they don't do. So it's like either we have a naming error, names in a way that is incorrect, and I think it's because we have inputs here but not decoder inputs. So I think I just have to rename everything that's input to decoder input, because that's actually the name here. Decoder input embedding, decoder input embedding. Right, so that was not enough. I don't see it.
And
Maybe
I don't know
why?
what we're doing anyway.
uh, Wait, so why does this? Oh, I see. Yes, this next. Hmm. Ah. Yes. Okay, I fixed it.
Magic.
Magic. Okay, so this instance is good now. Okay, so the only thing left here is the lookup mechanism again. So lookup decoder now needs entries for Bart. That is in line 520.
The lookup mechanism.
Is one
Oh
of
yeah,
these
the
orange.
names for the various layers. Sure. So we had model.encoder. We should have model.decoder. Decoder.layer.
Mm-hmm.
So stack of sbart decoder.layers, and then embed layer norm. Do we have one of those in the decoder? I need to scroll through 5 layers of decoder to know the answer. 6 layers, because there's 0 as well. Okay, after that there's... No, still layer 0. Okay, after that there's layer norm. Is that this layer norm? Embed layer norm? Yes. So decoder dot layer norm embedding. Oh, and this time they're both equal to pure, so I can't just copy. That will be harder. So embed layer norm for sbart will be equal to something of the string decoder.layer norm embedding, probably dot weight and bias. And if I search for bias, I'm sure I will find another example. Here,
Mm-hmm.
layer norm with bias. It's the 2 strings I just said, and EPS is presumably the same. I don't know what EPS is. Epsilon?
Oh yeah, epsilon. So the layer norm normalizes, right? So like for this, there's division involved, and in order to make that operation more numerically stable, there is a little bit of an epsilon that you add to the, I think, denominator, and this epsilon is configurable. We have to look it up later. It's probably 10 to the minus 5 or less. But it is we don't need to make it concrete here. It's just passed through the whole call stack.
Okay. So we don't have a non-embed layer norm.
Mm-hmm.
So layer norm of sBart is pure unit.
And we know that this is true, right? Because our type families tell exactly the same story, right? So like if we were to return anything but pure, we would get an error here.
Mm-hmm. And then dropout is the same everywhere. And then pos enc for Bart. Decoder dot, I assume, embed positions. We're not making use of embed tokens?
No, not at this point. So the thing is with embed tokens is that it's shared. So the encoder and decoder use exactly the same positional encoding. Interestingly, not the same positional encoding. So, I decided to make the token embedding part of the sequence-to-sequence transformer model, where the encoder and decoder are both fields, and therefore it doesn't appear here. You typed something weird there. Embed decoder, embed positions. I think you need to get rid of one of the embeds. I think the first one. Hey. Okay. That looks good. I'm not sure if I used fmap, applied m there everywhere. I think this looks nicer. Cool. That should work. Do we want to do the?
So we're done
sequence?
with the decoder and the encoder, with the encoder and the decoder. What else is there left after that?
There is the sequence-to-sequence model itself. So there's yet another. Wait a minute. I still have an error.
So the
in
bigger
decoder
thing
HS.
that runs, that includes the encoder and the decoder in the same way that both of those pieces contain a multi-head attention piece?
Wait a minute. It is. Sorry, can you repeat it? I was distracted.
I was just asking if the remaining piece, the sequence-to-sequence thing you mentioned, if that was a bigger thing on top, which surrounds the encoder and the decoder, and like maybe an extra step before, between, or after. It's not like a third piece somewhere. It's like it's a bigger piece.
It's the wrapper around both.
Cool.
Around encoder and decoder. Yeah.
So that's where we'll be adding the model dot prefix, I guess.
Indeed. So I opened that module just now. It's called sequence-to-sequence.hs.
Weren't you saying there was an error somewhere still in the decoder?
Yeah. Yeah. I think I can fix that error quickly.
Okay, I'll let you fix that error while I explore.
Okay, this was just a typo.
Cool.
All right, sequence-to-sequence HS.
Sequence-to-sequence something F. Their instances that I need to specialize. I don't see any. Oh, they are. I guess they're defined immediately afterward. In general, style. Okay. We just delegate.
That's right. I wonder actually if there's anything to do in this module, because these pieces are super generic. I don't think they are specialized at all.
Well,
you can search for Pegasus and just see what comes up.
Pegasus was using the encoder dot prefix, whereas we included the encoder dot prefix in the implementation of Bart. So I do think we need something different here. S Bart of, I guess, nothing, just a prefix.
Mm-hmm.
Unless the prefix does not already include model.
Yeah, let's assume it does not. It does. Yeah, I think that just prefix is fine.
Okay. So
Or we can also go back and erase encoder from that path. Doesn't
well,
really matter.
I think there was a reason why we did that. I remember that there was some parameter somewhere that was using an underscore instead of a dot, and that caused us some pain. But I don't remember if it was encoder dot, an encoder underscore instead of encoder dot, or if it was further in. I think it might have been further in, because I see here things like embed underscore tokens instead of dot tokens or something like that. But anyway, it works now. You can just leave it.
Okay, so how dot from this encoder? I'll just fix this quickly. I'm going just now and making the change so that we can keep it.
Oh, you want to keep the encoder dot? Okay,
Yeah.
sure.
Okay, make the change. Yeah, so just keep it like that. Also for the decoder, and then embedding we now have to be careful, because for the other models there was this. This is shared, and I think for Bart it is shared, and I think it's also called shared. So I think you can just exactly copy that line, and it should work.
So it would be model.shared, so at the very end, after the encoder and the decoder.
Yeah, it's at the very bottom.
Model.shared, wait, okay. Cool.
Can
Any other references
that
to
should
Pegasus in this file?
Probably not.
Transformer
Yeah, there's
equals.
something.
That's where we add the word model.
We could, yeah. Let's do it there. And then we have the language modeling head.
I saw that at the very top. Scroll. Layer 0, almost there. LM head.wait.
Yes. So no prefix.
No? Well, it depends on what LM head does. You think it adds LM head to its prefix?
So there's also final underscore logits.
Yeah.
And because of that, I think we should just say prefix here, because both of these pieces are actually part of the LM head. So this is actually the last module we have to
lookup LM head.
Yeah, just follow that thing. So if you command click on lookup LM head, you will be taken to.
That's the one part of Visual Studio I've nailed down. Go to definition, command click. Okay. So, dense. There's something called dense, but here we have something called logit bias and something called weight.
So just follow the Pegasus pattern here. So Bart doesn't have dense nor activation nor layer norm in its LM head.
All right. No activation either. No layer norm.
So the decoder is actually this element head wait thing.
Okay, and it has the same name as for Pegasus, and I'm head wait. And the bias is the other parameter, which is also called final Leggett's bias. So since they use the same name, I'm guessing that Pegasus and Bart are by the same team.
That's right. So we could...
So now we're done.
Almost. So there's some errors now because the type families have no entry for Bart yet. So if you scroll up, there is element head dense, element head activation, element head layer norm. So we need to just basically clone the entry for Pegasus everywhere.
Okay. Looks like that's it.
Okay, still errors? No.
Can we run it?
Almost. I just see something. So I went to the forward method at the very bottom of the file, and there's again a something that is incomplete, like a
Okay.
non-exhaustive thing.
So
And I think
bias, we do use bias.
but we don't use scaling.
Right.
All right. Wait, error. Where's an error?
I don't see
The
those
additional.
errors.
Oh, there's one more type family. Haha, there's element head output F.
I see the orange squigglies, but I don't see the red squigglies.
They're probably overlapping. Let me fix it quickly because I see the error here in front of me. Bam. Right. Cool. So can we run this now? Good question. So the test is still empty. I haven't defined it yet. So we would need to do that. But we also don't have a configuration of it, right?
Oh, with
So
all
we
of the
don't-
concrete numbers, yes.
Yeah. So if you go to that base thing, I think what we will need now is I think we can start from Pegasus. Let me just copy paste the Pegasus crap in there. Sorry, not crap. Let's call it numbers. And that would probably include all the language extensions that I use there, some data kinds and. Oops. What did I do? Oh, I copied it in the wrong file. Data kinds. Nice. Okay, so not Pegasus, we want Bart. Oh, there is no Bart model yet. And there's also no Bart model with language modeling yet. But I think we can just use the Pegasus code. So if I went here and I just copy, I'll replace everything that reads Pegasus with Bart, and everything that reads xsum with base. Then we have a good template. Of course, all the numbers are probably wrong, but
Okay, but you were saying that we're still missing some Haskell code, something called Bart model?
yes, so in common is empty. We need code in common.
What's supposed to be
but
there?
I think again we can use, yeah, so like if if you open a Pegasus common.hs, there is a bit of code in there. It's mostly glue code and some other defaults that are the same for every model in the Pegasus family of models. So what I would also propose here is just copy paste everything and renaming, and then see what falls through it correct. So let me do this quickly.
Okay.
Pegasus Bart. Okay. So now we have Bart model. Cool. So this should almost work. What troubles me now is that these numbers might be wrong. So I will quickly look them up on the Hugging Face webpage. So if you go to Hugging Face Transformers, no, actually Hugging Face Model Hub. This is where I want to go. Model Hub. You can search for models, and then if I type Bart, choose Bart base, go to config.json, I will see all the parameters.
One moment.
And
You're not sharing your screen, so I have to do the things you're saying, but it's taking me more time. So Facebook/BartBase.
yeah. Wait a minute. Maybe I copy it in the chat. Send message. Oh, Young was there as well.
Okay. So config.json. Lots of numbers.
Right. So I'm staring at common.hs in the Bart folder, and we have to worry about dropouts. This is probably 0.1 everywhere, but better make sure that it is. Then the positional encoding dimension. So I believe that should be 512. Oh no! So Bart has 1024. That is amazing. I didn't know that.
Okay. So that was max position embeddings in the config.json. Bart epsilon 10 to the minus 5. How did he call it in the configuration file?
It's not there.
Okay.
Did you see it? I did. So I guess we leave it at 10 to minus 5, which is the PyTorch default anyway. Okay. So we can be happy with this. Then we have another max position embeddings. This should probably also be 2024. This is the value though, not a type.
Okay.
The pad token is 1. It's not 0. Beginning of sentence. Does it have that in? Yes, and it's 0.
0.
And then the end of sentence token EOS.
2.
2. Wonderful. And then the attention mass bias, I think, minus 10,000. I've never seen a value different than that, so we can leave that.
Okay.
Okay, so that is the base configuration. So now the specific configuration for base. That was confusing now. So the common configuration is what we just did. Now we have the configuration for base. So we have to know how many layers in that base model.
So what's the difference between those two sets of numbers, of hyperparameters?
Yeah, so the common ones are the ones that are the same for all models in the Bart family of models. And the specific ones for the different sizes of models that have been published, so like base, large, whatnot, go into these other modules so that there is no name clash between them.
Okay, so even though like there's these 3 layers, there's the okay, I should not use the word layers, 3 levels of granularity of sameness the same architecture, the same hyperparameters, the same weights. This middle level of sameness is like split in two because there are some hyperparameters that I guess the original researchers didn't tweak, and one set that they did tweak. And so if we wanted, we could tweak all of those hyperparameters, but since we just want to reuse the snapshots, it's easier for us if we use two different files for those which they don't change and those which they do change.
Yeah, that's
Okay.
that's absolutely it. Yeah.
So
like we're making here the base one, right? But if we switch to large, we would likely only have to change the ones that are in base, right? So like number of layers, the dimensions of the heads, and so on.
And are the numbers still in config.json?
Yes.
Okay, so Bart base num layers. Add final layer, decoder layer, hidden layers. I will have to resize the window so it's not hidden by your face. I still see something that says the total number of layers. Are we supposed to add?
Yeah, it starts with encoder and decoder. So there's encoder layers and decoder layers.
Encoder layers 6 and decoder layers 6 as well instead of 16. Next, Bart base head dim. There's again encoder and decoder. There's attention heads. Is that the same thing?
That's that one. Yeah, attention heads.
So
12.
12. Oh, I didn't check if a decoder was the same. Encoder layer is encoder attention head is 12. Decoder attention heads is also 12. Encoder and decoder attention heads are both 12. Okay, next. Base head embed dim.
So this may be not in that file actually, which was this is derived number. Can you look for hidden size? Hidden size may be in here.
Yeah, I did see something called hidden size. Num hidden layers 6.
No, that's not it. Hidden layers? Wait. Num hidden layers.
You did not expect hidden layers? Don't know what those are.
This is odd. Okay. It's the model, the underscore model is what we're looking for. So this is 768.
Okay. Well, in the comments, wait, I think I might have modified the wrong one. Bart base head embed dim, not base embed dim, right? So instead of 64, we have a much bigger number.
So I
Is it this number that should be
everything
0?
that's 1024 in that file should be 768, I believe.
Okay, so I modified the wrong thing. This should still be 64, or at least we don't yet know what the number is.
Yeah.
But
so the hidden size is 768, and that model dimension is also 768. So now since there is this so number of heads times this DKV should be 768. So like if we divide 768 by 12, we get 64. So we should not change that number.
Okay, and is there any 124 in the file? No. Okay.
So now the FFN dims. So I think this should be 3072.
FFN, I saw that. FFN dim 3072 indeed. And
It's always a
vocab.
multiple of 1024.
Vocab size 50,000 instead of
Exactly?
96,000. No,
Ah.
56,265.
Right. I'm gonna change the docstring too, so that proper.
Mm-hmm. And then it instantiates Bart to something, to all of those numbers. Okay, cool. So now we can run it.
Cool. Now we can run it almost. So we need to write the test quickly, right? So I would
file?
start with the T. Pegasus.py. Pegasus.hs, sorry. So if I go into Pegasus.hs, there are like these three functions: test, Pegasus input, test, Pegasus decoder input, test, forward Pegasus, exon. I'm just going to copy those, put them in Bart.hs, do my usual renaming spiel, and then we're gonna have to choose inputs and outputs that we have in Python as well, so that we see them side by side. And then
and now the number of inputs need to match the size of the sentence, possibly with a lot of padding. So we can't just reuse the numbers you copied from Pegasus.
We could, but we also need the numbers in Python, right? Because otherwise we won't have a way of comparing them. Or I mean, you could try first to load the model and see that it fails. We'll probably fail. Then repair the damage and then go towards checking that the numerics are good.
So I
But
assume...
I'm getting a type error here at the moment. Pattern syntax in an expression. What? Oh, I need language extensions. That's why. Okay. Kinds. Sure. Nice. I'm fixing these bugs one by one. May take a minute or so. Okie dokie. Errors are gone except for two. So where are those? Found wildcard. These partial type signatures? Yes, okay. Variable not in scope forward. Oh, okay, there are more errors now. As initialize generator. Oh, Pegasus encoder output. So this should be Bart encoder output. And then we have search proximate equality. So Pegasus, this is Bart. No instance for has forward. Bloop, 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 bloop. Oh, seems like we forgot something. So I'm not sure if you're still following that the forward function is now where I'm having the last error in 949, and the error is no instance for has forward cross attention of Bart. So it seems like we didn't make a cross attention instance for our beloved Bart model.
Oh well, I was hoping that we were sufficiently close to the end that we could squeeze in.
So
You're cutting out.
They need it for the encoder. Are you still there? You're breaking up for me.
Yeah, you were breaking up as well. So I was saying that since it seemed like we were like almost there, that we could try to squeeze in running the numbers to get a nice finale. Either yay the numbers match or no they don't. But now since it looks like we still have some more work to do with this cross attention or cross head cross something piece, maybe we should do that at the beginning of next week and then run the numbers, and then we'll have a lot more time to play with the numbers and see what comes out of the model.
You could, yeah.
All right. So
far we made a lot of progress though, so like I'm very happy. And next time we'll also have the tokenizer.
Yeah, maybe next time we'll have the tokenizer.
Yeah.
Cool. All right. So thanks.
Cool.
And see you
Yeah,
next
that
week.
was fun.
Ciao.
See you. Bye.